Hello, Gen Chem Nation. We are talking today about solutions. We've already talked a little bit about solutions in part 1 of general chemistry, and now we're going to get into a lot more detail with the second piece of this idea of solutions. So let's just kind of walk through some terms. I'm hoping that this is review for us, right? We have the solvent. The solvent is, the substance that is doing the dissolving. This is called the dissolution process. We also have the solute, which is the substance that is being dissolved. Our solvent phase is going to be specific, but I want us to understand that, while all phases can act as a solvent, we will just focus on solids. We will just focus on liquids. So we'll be, a little bit more specific with that solvent phase. Our solute phase can be any, though. Alright, so we can have solid solute, we can have liquid solute, we could have gas solute in terms of the phases of the solute, the molecule that's being dissolved. And that creates the solution, which is simply the combination of solute and solvent. So, in talking about solutions, we have some terms we should know, such as, there's things known as a suspension. Suspensions are where not all the solute is dissolved. And it is suspended in the solvent. So, this is termed as a heterogeneous mixture, but it's just kind of this suspension because of the nature of what it looks like. We have dilute. Solutions. Dilute solutions is where the solute is not very concentrated, or not much solute is dissolved, and more solute can be dissolved if added. Remember, dilute solutions which are not concentrated, are produced from stock solutions. Which are very concentrated. Now you might remember the idea of M1V2 equals M2V2 as far as that goes. So for dilute solutions, mainly the big thing is that more solute can be dissolved. Right? We can actually put more of that solute into solution. We also have then saturated solutions. And this is where no more solute can dissolve. Into solution. And this is a temperature effect, but our temperature, we're usually around 25 degrees with this idea of saturated solutions. So no more solute can dissolve once you get to saturated solutions. We then can get to super saturated solutions. And this is where more solute can dissolve past the saturation point. By raising the temperature. Of the solution. So basically past that saturation point, and it kind of takes me back to when my mom used to make iced tea. She would make iced tea. She'd get the tea bags hot water. She had a ton of sugar into the hot mixture. All the sugar would dissolve, and then she would pour it over ice and put it in the fridge. And you could literally see just, the sugar crystals precipitating out of solution as a result of that temperature shock. But so, going past the saturation point is doable, but we need to raise the temperature. But then realize once we go back and we lower that temperature, that we will then start to see solid or precipitation occur to create now, more of a heterogeneous solution as opposed to homogeneous. We also have terms such as miscible. Miscible is where, two molecules are soluble in one another. You could really think of this as, homogeneous, as well, but just a slightly different term describing the same thing. And then we have the opposite, which would be non-miscible, where, we have two molecules that just aren't soluble. Right, and we used to say, heterogeneous. So those are the basic terms that we have as far as looking at, solution chemistry, and getting into units. We have a bunch that we should remember, right? Percent by volume is one, where we would have the volume of our solute over the volume of solution times 100. We can also represent that as a mass percent as well, with mass of the solute over the total mass of the solution times 100. We've used those in the past. Some other big ones would be molarity, right? Molarity, remember, is capital M, and that's moles of our solute per liter of solution. And we also have molality. Molality is little m, and while the numerator is the same, notice that the denominator is different. Right, in one case it's liters of solution with molarity, and in the other case it's actually kilograms of solvent. So not only is the unit changing, but also what the unit is describing is also changing. Some ones that we won't utilize too much, if at all, but just so that we're aware of them. One is known as normality, and no, it's not how normal you are, but it's one that we tend to see a little bit more in bio, which is specific to acids and bases, where we have moles of protons per liter of solution. So kind of like a molarity, but subtly different in that it's specific to moles of H plus as what's considered the solute. Some other ones that we won't really see too much of, the ones that we're going to see a lot are ones that we've been talking about here as far as our volume percent, our mass percent, our molarity, and our molality. And so these are, ones that we will see, a lot of. And then the ones that we don't see too much is the normality, and then also really, really dilute solutions, such as, parts per thousand, or PPT. These types of parts is really like a mass percent. So you'll see that we have mass of solute over mass of solution, but we're multiplying it by 1,000 or 10 to the third. So these are for really, really dilute solutions, solutions that we'd be more like looking at, pollution in rivers and things of that, oceans, where we have hazardous materials, but they're in extremely small quantities due to the fact that our solvent or our solution is so large. So we can kind of keep running the gambit here as far as our parts per thousand, and then we can go up a level to something that's even more dilute, which would be parts per million, right? And then even we can keep going, parts per billion, and then we can even go to parts per trillion if we want to, etc. And so that's 10 to the ninth. And so these are often used really in environmental type talking about environmental concentrations or environmental sampling. So those are all the units that we have for the chapter and dealing with solutions. As I said, we're gonna see these other ones such as PPTs and PPBs, but we're really focusing in on mass percent, volume percent, molarity, and molality. So that takes us to the next section, which would be now getting into prediction or predicting solubility. You're kind of asking the question is, will it dissolve? So our first rule would be to look at phase of the solute. What we find is that if you're looking at liquid solute versus gas solute, or liquid solute versus solid solute, liquid solute tends to be more soluble in a liquid solvent. So that's one way, predicting, something to be more soluble than another is by just looking at the phase of the molecule. Otherwise, it's just kind of a matching of forces of attraction, and even within the realm of, liquid gas or liquid solid solutes, we still want to try to think about, matching forces of attraction. So if we have small molecules with polar groups, polar groups being groups such as OH or NH, any of these types of electronegative types of groups, fluorine, carbon, oxygen double bonds. These small molecules with polar groups are soluble in water due to matching hydrogen bonding forces of attraction. But we got to be careful with that idea of the small molecule. As you increase the number of carbons within a molecule, you start to see a decrease then in that solubility. And in fact, once you're looking at greater than 4 carbons, diminished solubility is observed, or diminished water solubility is observed. For molecules that contain polar groups, but are, or contain rather, carbon count greater than or equal to 4, then a polar molecular solvent is preferred. So we got to be careful of those types of rules, that we see in terms of our H2O, right? We're looking for, small molecules. We're looking for polar groups, right? These are ones that are soluble in H2O. But once you're greater than 4 carbons, diminished water solubility is observed. And then from that angle, now we want to just pick something that's, really a polar molecular solvent. Once our carbon count is greater than 4 carbons within a molecule. So some examples of, polar solvents would be such as, chloroform, dichloro, methane. We have, a number of these chloro-containing, solvents. Ethyl acetate is kind of another one, but I think that's getting a little bit too far, reaching for us. But, here are a few, and notice that these are all polar molecules, right? These all have dipole forces of attraction. And so that's why they would be, paired very nicely with a polar solute. So that, you're matching forces of attraction within that system. For molecules that don't contain polar groups, then a nonpolar molecular solvent is preferred. And so that's just kind of the matching of forces of attraction. So if you don't contain any polar groups, now a nonpolar molecular solvent is the preferred choice. So, as some examples of that, we could say, methanol, dissolves better in, and we have, a couple different choices. we have, ethanol, we have dichloromethane, and we have, let's say, carbon tetrachloride as examples, right? And so here, we should just kind of match our forces of attraction. That's kind of the way we want to go about it. We have hydrogen bonding for our solute. There we have a match with hydrogen bonding for the ethanol. We have dipole-dipole for the dichloromethane. And then we have dispersion for the carbon tetrachloride. And so it's going to dissolve better in the ethanol because we have the, like dissolves like. If we do another example, let's say molecule looks like this, and we have our choices of H2O, and we can put these phases in above if we want, as far as all these are liquids. So we could say H2O, and then we could use maybe the same other choices of solvents like the dichloromethane, the carbon tetrachloride, and so again we're asking, what does this molecule, dissolves better in? And if we start the matching game, we might be led astray. We see water matches our force of attraction within the solute. They both have hydrogen bonding forces. And then the other two are the same, right? Dipole and dispersion, as we talked about above. The problem is the carbon count. And so even though this is a hydrogen bonding molecule, it also has dipole-dipole. And it has greater than 4 carbons. And so really, because of the 4 carbon motif, is why we lose our water solubility. And so we would pick then a molecule that then supports the dipole-dipole forces of attraction. And so we see greater solubility there. Or if we did an example such as, propane, and so, what does it dissolve better in? We could look at, H2O, again, CH2Cl2, and then carbon tetrachloride. And so if we look at our forces of attraction, we have dispersion for propane, hydrogen bonding for the water, dipole for the dichloromethane, and then dispersion for the carbon tetrachloride. And so there is our best choice. Seeing there, the like dissolves like motif. So sometimes it can be a little bit gray, especially with that carbon count, but most often you're just matching forces of attraction in terms of polar versus non-polar, or looking at hydrogen bonding as well. For For solids, ionic solids prefer H2O or water as their solvent of choice. Ionic solids are more soluble the weaker their electrostatic forces are. So remember, for strong electrostatic forces, we have, one greater charge, and then two would be, same charge, then smaller ion size leads to stronger electrostatic forces. So if we were looking at, sodium chloride versus magnesium iodide, and ask the question, what would dissolve better? In H2O, we would answer sodium chloride. Sodium chloride here has weaker electrostatic forces due to smaller charge. So in the case of the sodium chloride, we really have, a +1, -1 type of system. While with the magnesium, it's really a +2, -2 system, with the two iodides, make each one being -1. So we want, weaker forces within that solid substrate so that it dissolves easier. For molecular solids, you just want to match forces of attraction. Almost last in this type of prediction, for gases, the molecule that has stronger forces, i.e. that could be like, larger boiling point. So the molecule that has stronger forces is more soluble. And this is still a, like dissolves like scenario with the forces of attraction. So if we were looking at, an example of carbon dioxide, and what it dissolves in better, it dissolves better in, let's see, a choice of solvents. We could have dichloromethane versus carbon tetrachloride. And if we identify the forces, carbon dioxide would be dispersion forces. We have dipole for our CH2Cl2, and we have dispersion for our other solvent, the carbon tetrachloride. And we see the match here with the carbon tetrachloride. So that's the gases. So that's all the phases, really, pretty much. It's really all a like dissolves like idea, but sometimes we're looking for weaker forces, like with solids, and then sometimes we're looking for stronger forces, as in with gases. The last one is temperature effects. And an increase in our temperature is going to result in increased solubility of liquid and solid solutes. However, decreased solubility in terms of gases. So with temperature affects an increase in temperature, we have increased solubility in liquids and solid solutes. However, we see decreased solubility in terms of gases. And we talked already about the increase in temperature with like solids or liquids, right? This idea that, we can go past saturation and create supersaturated solutions as a result of temperature. As far as gases, that might be a harder one to understand as far as, why are they less soluble at higher temperature? And that just has to do with the relationship of kinetic energy in gases that you might recall from Module 10 and our gas laws, that the kinetic energy of gases is dependent on temperature, that there's, with an increase in temperature, there's also an increase in kinetic energy. So as our temperature increases of the solution, it just becomes harder and harder for the solvent to trap the gas. And maybe I'm sure we probably all have observed this. I'm sure we've all been bored enough to watch water boil, right? Or, we're hungry, we're bored, we're cooking some mac and cheese, and, our first step is to boil the water. And if you watch it, right, you'll notice that, way before boiling actually occurs, you should start to notice little bubbles coming off of the bottom of the pan. But yet it's not boiling, right? Just these little bubbles that are kind of escaping from the bottom. This is called degassing. And so as you're raising the temperature of the water, you are now, seeing decreased solubility of the gases in the solution, meaning that some of the air is solubilized in the water. We know that because of aquatic systems, right? We have oxygen dissolved in the water, we have nitrogen dissolved in the water, etc. And so as we raise that temperature of the water, we now start to see these little bubbles come out, and that's actually the air gases, the oxygen, the nitrogen, etc., now escaping the actual solution. So that's that notion of temperature effects. And here we see the temperature effect. We've taken some water, increased its temperature, and we can see all these little bubbles emulating. That's loss of solubility of the air in the water due to an increase in temperature.